All right, so this password hash one gets you started. As you may know, Microsoft password hashes use a very simple system because it's very, very old. Microsoft password hashes were defined in 1993, and in those days, there wasn't even MD5 hashing yet, so they use MD4. So if you want to calculate a Microsoft password hash, everything is easy in Python because other people have written libraries that do pretty much anything you want to do. So there's a hash library available. And so let me make this program, nano hash.py. All right. And what this one does, it imports the hash library, and then it does takes the word password, encodes it, and so it moves into a byte object and then hashes it with MD4. So let's try that. Python 3 hash. All right. Well, now I didn't get what I wanted. I didn't see a hash. I have the address of a hash object because this creates a hash object. But to see the address, I need to run it through the hex digest function to give me the usual base 64 output that I was looking for. So let's put that in there. Excuse me, hexadecimal, not base 64. All right, now I've got a hexadecimal output. So it looks good, but the problem is it's wrong. The correct password hash of lowercase password is 88 in Microsoft. Starts with 88, and this is wrong. And the reason it's wrong is the same thing I mentioned before. Windows was a very early international operating system, and so everything Windows does is encoded with an old version of Unicode, which is UTF-16LE. So Microsoft encodes the password with that version of Unicode before hashing it. So I'm going to put in that code instead. So now it has to do password. Try to make it fit on my screen better. There. Yeah, now it does password and encodes it with this old version of Unicode, and then I should get the right value. Now I get the 8846, which is the known hash of password hashes, of Microsoft password hashes. So you can make a loop that calculates all the hashes for 2-digit passwords, and then you can make passwords in this pattern. I have a pattern with just a 2-digit code, and these are real password hashes from a real Windows machine. So these are Windows NT hashes, and so you can crack these passwords. There's only 100 options to try for each one. And then you can see how even adding more rounds doesn't make it very hard. Using a normal password hash for passwords like this is a really bad idea because these password hash algorithms were designed to run really fast, and that means an attacker can try millions of guesses. What you want is a password hash that is really slow, and that's what Linux and the Mac use, but Microsoft has never updated their stuff. So instead of like one round of MD4, here's MD5 with several rounds, less than 100. So you're going to have to try all the numbers of rounds. You hash it, and then you hash the hash, and you hash the hash again to get these. And down here, you increase the number of rounds of MD5 even more, and then you put in some rounds of SHA-1. And even though you don't know how many rounds, you'll find that it's not that hard to do, and it doesn't take too long because these password hash systems are too fast. All right, and here's Linux password hashes. To compare, these are Debian 10 hashes, and they use this algorithm called crypt. So you can try cracking into that, and what you'll find is you can still do it because there's only 100 options, but it is much slower and much harder. And here is Lastpass. Lastpass uses a salt, random characters added to it, and then 100,000 rounds of server-side SHA-256. So again, you can crack them here, and since there's only 100 possible passwords, you can still find it, but this is really pretty secure. The default in Linux is 5,000 rounds of SHA-512 plus a random salt. And Lastpass tries to be more secure by using 100,000 rounds. All right, and I think while we're here, I think I'll just mention the row method. This technique where you hash something and then you hash the hash and you hash the hash again is they're called Pollard's row. So you calculate the hash of something, then you hash it again, hash it again, hash it again. And what happens is eventually you'll have a hash collision. Eventually, at some point, you'll have a value you've seen before. And when that happens, it will just go in this loop. And the amount of time it takes for that to happen is approximately the square root of the number of possible hashes. This is why hashes have to be so long. MD5 was 128 bits long. And so you would expect to have to calculate 2 to the 64 hashes before you'd find a collision. It turned out that that wasn't a big enough number at all, and that there were weaknesses in the algorithm. So we moved to SHA-1 that was 160 bytes long, 160 bits long. So it should have taken 2 to the 80 calculations to find a collision. But once again, there were weaknesses in the algorithm, and they were able to find it before that. And a couple of years back, Google found a SHA-1 collision. So now we're all moving to SHA-2. And SHA-2 is typically used the 512-bit version, or the 256 is the shortest one. And so those don't have a known mathematical weakness that matters yet. And you'd have to do something like 2 to the 128 calculations to find a collision. And 2 to the 128 is an impossibly huge number. All the computers in the universe running for the age of the universe would not be able to do 2 to the 128 calculations. So until they find a shortcut of some kind in the algorithm, SHA-2 hashes should be pretty good. But if they fail, we have SHA-3 already defined to replace them. But anyway, here you get to try this where you calculate some hashes with various simple systems and find the place where the loop hits. So I'll stop this one.